Hi viewers, welcome to LMS Solution. Today we are going to see about optimal network reconfiguration in the power system by using optimization method. So that optimization method used to for reconfigure that power system network for minimize the power loss and then to enhance the voltage profile in the distribution system. Okay. So for that I am taking this reference paper. So in this reference paper they are using 33 bus system. Okay. In 33 bus system they are going to apply network reconfiguration. By applying network reconfiguration they are going to find out the uh, that uh, tie switch configuration. Okay, so which switch going to be opened before and after optimization method. Okay, to reduce the power losses in the 33 bus system as well as for enhance the voltage profile in the 33 bus system is implemented in this was implemented in this paper. So here you can see that this is the network diagram. So in this network diagram we can see that there is 5 loop, right? Loop 1, loop 2, loop 3, loop 4 and loop 5. So in this loop we can see that tie switch is connected in the here, right? 33, 34 and 35, 36 and 37. Actually this switch is initially is opened, okay, in this network, right? After that we are going to apply that in PSO, selective PSO, particle sum optimization. Okay, so after applying that selective particle sum optimization, so you have to find out so which switch going to be sectionized, that means you have to open. Okay, so that going to be taking care of that optimization method for minimizing the loss and then maximizing that or enhancing the voltage profile in the all buses. Okay, so for that they have some equations. So here you see that, right? They are formatting that objective function, okay, for network reconfiguration. So here you see that, so this is the objective function they are considered for applying that network reconfiguration to minimize the power loss as well as enhance the voltage profile. So for that they are taking that loss, right? Real power loss, reactive power loss and then CVD. Okay, so CVD nothing but the deviation, voltage deviation. Okay, so deviation will be calculated like this: 1 minus VI. So VI nothing but power, bus voltage for the bus voltage in the each bus in the 33 bus system. Okay, so PL is active power loss and QL is reactive power loss. Okay, so next you can see that there are having some constraint, right? The voltage should be in between this minimum maximum limit. Okay, and then we have to maintain that reactive power limit, line loading limit, load connectivity. Okay, so these are the things we need to follow to implement that logic for finding that optimal configuration. Okay, and then this paper they consider three case studies, right? That means 4 case studies. One is base case, another one is they are considering light load condition and normal load condition and then heavy load condition. So base case means we are not applying any reconfiguration. Okay, so just you are taking the IEEE 30 bus system and then you have to find out the power loss. Okay, in light load condition we have to apply that optimization, right? Selective particle sum optimization. So they are considering that 50 percentage of the normal load, right? So you have to take the 50 percentage of the normal load and then you have to optimize the network. Right? That means you have to find out the switch, tie switch, right? For opening, right? By using PSO with the 50 percentage normal load, and then we for normal case, base case, right? You have to apply that optimization. You have to find out the switch details, and then heavy load they are considering 130 percentage, right? So 1.3 times of the normal load you have to apply and then you have to find out. So you have to find out the That means you have to find out these losses. Okay, so here you see that you have to find out total loss and then loss reduction and voltage profile detail. Okay, and here you see that, right, single line diagram after optimal network configuration. Okay, so here you see that this dotted line. So in this paper they find out that open, that means sectionalized switch will be 7, 11, 28, 32, 34. Okay, so here is the 7 will be shown in dotted line and 28 will be shown in the dotted line, 32 is shown in the dotted line, so 11 is shown in the dotted line. Okay, so this is a final sectionalized tie switch, okay, for the optimal power flow in the IEEE 35 system. They find out from that selective particle sum optimization. Okay, so for we are going to implement this same logic in the MATLAB here. So I am going for that MATLAB program. So here you see that, right. So in order to implement this program we need a math power. Okay, so here we have math power tools. Okay, so you can download that math power document from the website, that math power website. Okay, so just you go to type in Google, right, math power download, so then you can download from this website. Okay, for the math power 8.0, so whatever the latest version you can use that one. Okay, so I already downloaded that one. I am using math power 4.1, the old version. Okay, and then from there you have to take that case 33 detail. Okay, here you see that this is a case 33 detail here, that means IEEE 33 bus detail I am taken here. And then so initially we have this one, I will later explain this one. So here we are fixing the loading. Okay, so I am fixing 50% of load. Okay, and then number of particles, number of dimension. Okay, number of dimension means how many switch to be opened, right? That means how many switch we need to tie switch need to be open in order to minimize the power loss and to enhance that voltage profile. And then the initial particle position we have to load, so that only we are having here. So this initial position, so all position will be, that means initial opened switch. Okay, so that detail will be have the similar thing, so initial one only. Next we are generating a random velocity, that means we are taking old equal to that means initial velocity, population best, global best. So these are the random values. Okay, so initial fitness will be, we are taking 0, that means initial best value we are consider 5000, sorry, 50,000, and then convergence detail. Okay, that means we are need to plot that convergence graph. So for that we are taking initial will be 0, and then here we are fixing the PSO parameter, right, W max, W minimum, and the inertia weights. That means these are the W max, W minimum, nothing but inertia weights. Okay, and then we are consider maximum iteration is 100. Okay, so this is tapping, that means loop positions, right. So we are taking loop position, and then we are going to find out the create the incidence matrix here. So next we are going to applying the PSO optimization. So okay, so here you are applying PSO optimization. The PSO optimization will be generate the that open position details, and then that will be that going to be processed to that network, and then we are going to execute that math power flow, and then we are calculating the fitness here. So here you see that, right. So here we are calculating the sum of real power, sum of reactive power, and then here we are calculating the voltage deviation. Okay, and from that we have to calculate the, this loop will be keep on executing. Okay, so this selective particle sum optimization is keep on executing, and it going to be find out the optimal position, optimal switch details. Okay, so finally after executing this one, here we are executing the normal case. Okay, so here that means base case we are executing here, and then after that we are applying that actual case details, and then we are combining the plot for the base case and optimization case, okay, after before and after reconfiguration. And then here we are plotting that convergence, okay, finally we are displaying the results, okay. So this code used for that reconfiguration of the power system in the IEEE 30 bus system. Now I am going to simulate this one, then you will get the idea. So now we are applied a light load condition, okay. So now you see that, right, it keep on executing. So this will be going to be find the configuration detail or tie switch detail after optimization, before optimization, and also you will see that power loss, everything. So this is the convergence graph we are getting for that light load condition. And here is that this the tie switch, initial tie switch open to position, that is 34, 35, 36, 37, okay. So here is the tie switch after optimization will be 7, 13, 17, 28, 35. So initial power loss will be 48.53 and power loss after optimization is 36, okay. And then here the power loss reduction is 24.57 and minimum voltage before and after optimization you will see here, right. And also you can see this plot, okay. So here the blue color is the base case and red color is the optimized case, okay. So you will see that variation, right, profile will be improved, okay. So you have to run this simulation for that means 50 trials, and then from the 50 trials you have to find out the optimal solution for the light load condition. So next I am going for base case with optimization. So just I am going to execute this one. So once optimization is completed, then you can see that results in command window. So now you see that, right, this is the result 7, 10, 14, 28, 36, and then power loss is 208.45 kilowatt before, and then after optimization is around 142.433 kilowatt. So power loss reduction is 31.67, and then you can see the minimum voltage before and after optimization. So this is a graph, okay. So this kind of graph also you can see in this paper here. So this is a normal load condition. So this is the result. So what result we are getting? This is the result we are getting now. See that? And then this is a convergence curve, okay, graph for that normal load condition. So next you go to normal load condition where that result will be 7, 11, 28, 32, 34, okay. We are getting around 7, 10, 14, 28, 36, okay. So also you are getting this result. So you need to reconfigure that means you have to try this simulation for 50 trials, and then you have to find out the optimal result from the 50 trials, okay. So next move on to the heavy load, right. You just to type 1.3 and then you can run this simulation. Then it going to be optimize the parameter. So finally we will get the optimal result, okay. So wait for some time. So it will take some time for execution, because it's solving the problem, okay. It's solving that problem, okay. Here you see that, right. So this is a final configuration, that means which switch going to be opened, right, 2, 34, 35, 36, 37. So here you see that we are getting this kind of result, okay. So you must try for several times, okay. If you try for several times, that means you have to try for a number of trials, because this is optimization method, but it start from the initial constant position only, constant initialization only, even though. So we need to test this system with several trials, okay, then only you can find out the result. If suppose we are not getting this result right correctly, then one thing you can do here is you skip this portion, okay. Only you take that power loss, real power loss alone, okay. So just you have to skip this one and run this one, okay, then you will get the result. We are going to take only the power loss as a fitness function, so we will get the better result, okay. So better you can take only real power loss as objective function and then do that optimization, then you will get the better result. So here is that, right. So before optimization, after optimization, right. So before will be 369.4 kilowatt and after will be 241.65 kilowatt, okay. So here you will see that comparison of both results. For here is that the blue color is the before optimization, red is the after optimization, okay. So because we tried that paper, but only one thing, during heavy load condition, right. So we cannot use that this subjective function, okay. Where is that? Yeah, this one. Yeah, so we cannot use this objective function because when we are using this objective function, it's violating this one. Otherwise we need to take absolute value. If suppose we are going to take the absolute value of this real power and then absolute value of reactive power and then absolute value of voltage deviation, okay. So if suppose we are taking like this, so it might be solve this problem, okay. So now I am taking the same problem, that means same objective function, but now we are considering that absolute value of the power loss, real power loss, reactive power loss and voltage deviation, okay. So let me try this now because we need to solve the problem, right. So we need to try the several method, because when you are considering real power loss alone, right, we are getting the result, that means the power loss will be reduced after optimization. So when we are not considered without absolute value, right, that means we are taking that real power loss, reactive power loss and voltage deviation, then it will be having problem. Now you can see that, right, now we are getting the result. So now we are taking that absolute value of that real power, reactive power and voltage deviation, then it will be work now, okay. So let me again I am going to test the system with a different loading condition, okay. So 1.3, first we check the 1.3 details. So here is that this is the result we are getting now. So this is a before optimization and red one is after optimization, and then here this switch open portion, that means final optimized result for the switch 3, 18, 13, 22, 32. The power loss will be 369.4077 kilowatt. Now it is 166.2846 kilowatt. So and then you can check the paper result also. Now come to paper and here you can see that, right. So proposed method they are having 226.82, but so this result will be very, that means our result is very less now, okay, when compared to paper result. So we are getting better result. So next I am going for a normal case, okay, that's just I am using normal load case and then I am going to check the result. So when we are going to apply any optimization for a minimization function, you have to modify the fitness function correctly, then only you can get the proper result, okay. So first you try with that whatever you are seeing that paper, right, just you try, and then after that you have to slightly modify the result, that means objective function correctly, then you will get the result. So now we are getting this result. So before and this is after, red color is after, and then this is a convergence graph. Let me go that here, right? So here it will be 112.58, but we are getting around 146. Okay, so for normal case we are getting highest value, but we need to, that means we need to keep on executing this program for several times, then you will get the result. So now I am going for light load condition and check the result. So light load, they are having 32 kilowatt, power loss will be 32. So we will check that our result. So we are getting 33. Okay, so that means around 1 kilowatt loss variation we are getting now. Okay, but we are getting almost that nearer to that result of that paper. Okay, so this is a result of this optimal reconfiguration of the power system for power loss reduction as well as enhance the voltage profile in the IEEE bus by using selective particle sum optimization. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you so much. Bye bye.